So in this video, I'm going to talk about a couple of simple models for flux density in multiple dimensions. And I want to first start by just reminding you about models for flux density in one dimension. Right? In one dimension, we talked about flux due to diffusion. Right? And what we said for flux due to diffusion was that if we had some pipe of cross-section A and a sort of material that had a diffusion constant d, that the flux density is that cross-section area times the diffusion constant times the partial derivative of the concentration with respect to position with a negative sign. Okay? Which basically was a way of saying that if I have, say, some quantity of stuff versus position that looks like this at a given time, a little while later it's going to have spread out. Right? It's going to look a little bit more like this a little while later. So there will have been a flux in that direction and a flux in that direction. So on this right-hand side, the function is decreasing. So the partial of n with respect to position is negative. I get a positive flux in that direction. And on this left-hand side, I get a negative flux. The function is increasing, and so the particles go from higher density to lower density. So that's how we did sort of the one-dimensional case of diffusion. I want to note here that, in fact, I could have written this as being A times minus d partial n with respect to x, so minus the diffusion constant times the partial with respect to n, and we could have called this the flux density in 1D, because if you look at the units here, this is number of particles per meter squared per second, right? Times meter squared is the cross-sectional area, so this ends up coming out to a flux as number per second. So this quantity d times the partial of n with respect to x is what we'd refer to as the flux density. Okay? And we also introduced the idea of an advective flux, so the flux due to advection, right? And we said that that was the cross-sectional area times the density of particles times the velocity at which they're moving. So the sort of idea of that is if I have some number of particles versus position and they look like this, but the material is that the fluid that they're in is moving, the particles are going to move along so that sometime later they look like that. So this motion of particles due to bulk motion is the advective flux. Of course, I've already written this in a way that is not just one-dimensional. I guess I shouldn't have made this a vector, but you can certainly imagine how as soon as you go to multiple dimensions, the sort of one-dimensional version, which would be a times n times v, just as a positive or negative number would turn into a vector quantity. So that's how we think about both advection and diffusion in the one-dimensional case. The two- and three-dimensional cases are not terribly different. So let's start first with the advective case, because that's the same. In multiple dimensions, the advective flux density, right, is simply the particle density, or the density of the physical quantity, times the velocity, right? And you can see that that's what it ought to be right here. This would be the flux density for the sort of one-dimensional case. And so this is saying that basically when you've got the fluid moving at some velocity v, or the medium moving at some velocity v, that you're going to get a flux density in the direction that the fluid is moving, right? Maybe a little bit more complicated is the idea that of how diffusion works in multiple dimensions. The diffusive flux density is again minus a diffusion constant, but times the gradient of whatever that concentration, whatever that sort of particle density, or whatever the physical quantity is. And that requires a little bit more thought to think about. But if you sort of draw, say, a contour plot, so let's say I've got some concentration of particles that's really high here, and then it drops off as I get further away. If I think about what the gradient of this looks like, well, gradient always points uphill, right? So the gradient always points in the direction of increasing concentration. And the diffusion current, or the diffusion flux density, will always point in the direction of decreasing concentration. So the actual flux due to diffusion is always going to be opposite the gradient, right? So flux, the diffusive flux sort of goes downhill, the gradient points uphill, so that's why it is proportional to gradient, and it's also why you've got this negative sign here. Okay? So there are certainly other ways that you can think about flux occurring, but diffusion and advection are really sort of the primary models that we talk about. So with these two in mind, we can now go on to write out the sort of general partial differential equation for a sort of multidimensional case. So we've got the time rate of change of some physical quantity, right, locally. So the partial derivative of this physical quantity, this might be the particle density, it might be something else, right, is minus the divergence of the flux density. Well, the flux density contains two terms, right? One is the diffusion constant times the gradient of the concentration, and that should be F, since I've got an F on the left-hand side, right? And the second term would be the concentration of whatever the quantity is times the velocity that the medium is moving at. Okay? So we end up having two terms. This is my diffusive flux density, and this is my advective flux density and flux density. Okay.